Hey everyone, Powell here. In this video, I'm going to show you what to do when you are verifying trigonometric identities when there's factoring involved, specifically when you have to factor polynomials with sines and cosines. So the first example we have here is kind of a curious little problem where it says sine to the fourth x minus cosine to the fourth x equals sine squared x minus cosine squared x. So if we look at the left-hand side, I'm going to make the left-hand side look like the right-hand side. Usually you want to make the more complicated side look like the simpler side, and I guess squares are a little bit simpler than fourths. So on the surface this looks a little strange, but this is actually a difference of two perfect squares. And just a review, if I have a squared minus b squared, that equals a minus b times a plus b. Now to go further with that, if I have a to the fourth minus b to the fourth, that's also a difference of two perfect squares, a squared minus b squared times a squared plus b squared. So this is the one that we're going to specifically look at in this case. So going back over here, I can expand sine to the fourth x minus cosine to the fourth x as sine squared x minus cosine squared x times sine squared x plus cosine squared x. And that's going to equal, move this over a little bit, and that's going to equal sine squared x minus cosine squared x. Now looking at what we have on the left-hand side, there's nothing I can do with sine squared x minus cosine squared x. That is a difference of two squares, but we don't need to factor that in this particular case because taking a look at this here, no, that's not what I wanted to do. Taking a look at this here, I know that sine squared x plus cosine squared x equals 1. I know that because my Pythagorean identity says sine squared of an angle plus cosine squared of an angle equals 1. And that's exactly what I have. So it doesn't matter what x is in this case, that equals 1. So this is sine squared x minus cosine squared x times 1 and anything times 1 is itself. So we have sine squared x minus cosine squared x equals itself. And we verified that identity. So that's a case where if you see two things subtracted and they happen to be perfect squares, you know it's a difference of two squares and you can factor it like that. And I also think it's cool that a binomial in terms of fourths is the same as in terms of squares. That's really funny. It's funny to me anyway. Now let's look at this one. This one's a very curious example and it has a little bit of a twist at the end. And this is also one of those rare cases where, as I said, usually what happens is you want to turn the left-hand side into the right-hand side. That's how a lot of these questions are set up. But the left-hand side is a lot simpler, so I'm going to work with the right-hand side and get it to look like sine to the fifth x cosine squared x. Now the first thing I'm going to do is that trinomial with cosine in the parentheses, I'm going to put that in standard form, meaning I'm going to put it in highest degree to lowest degree. So this is going to equal cosine to the 6x minus 2 cosine to the fourth x plus cosine squared x times sine x. Now, that looks frightening on the surface because we have to the 6th power, and that's very strange. But what I'm going to do is factor out the greatest common factor of that trinomial, which is cosine squared x. So this equals cosine squared x times cosine to the fourth x minus 2 cosine squared x plus 1 times sine x. Now let's take a look at this trinomial here. On the surface this looks scary, but let me rewrite it. Instead of using cosine x, let's look at it in terms of x. Let's say it was just x's instead of cosine x's. This isn't so bad to factor. In fact, this quartic trinomial factors just like a quadratic trinomial. I have x squareds that would multiply to get me the x to the fourth. I have negative ones that would multiply to get me the positive one, and the outside terms times the inside terms gets me negative 2x squared. So, and then that would equal x squared minus 1 squared. So that's not so bad. This same trinomial in terms of cosines is exactly the same thing. Instead of x squared minus 1 times itself, it just equals cosine squared x times itself. Or, I'm sorry, cosine squared x minus 1 times itself. So it's really just the same thing as if it were terms of x. I think just because it's cosine x makes it look a little scarier. And then I'm going to rewrite the line again, but instead of cosine squared x minus 1 times cosine squared x minus 1, I'm going to write it as cosine squared x minus 1 squared. There's a specific reason we have to do that, and that's where that twist I mentioned comes in. So, cosine squared x minus 1. We have something that looks close to that. If we go again to our Pythagorean identities, there it is. I have sine squared alpha plus cosine squared alpha equals 1. I'm going to take that identity and rewrite it down here. And I'm going to get the cosine squared x and the 1 on one side. So I'm going to subtract cosine squared x from the left-hand side to the right-hand side. So this becomes sine squared alpha equals negative cosine squared alpha plus 1. Those don't look quite the same. In fact, in one, the cosine squared is negative and the other one is positive, and vice versa for the negative, or for the 1 rather. So what I'm going to do is multiply both sides by negative 1, so I get negative sine squared alpha equals cosine squared alpha minus 1. Now that identity works, and that we can plug into our equation we have over here. So this now becomes cosine squared x times negative sine squared x squared times sine x. Well, I have negative sine squared x squared. This is where it gets weird, because if I take negative sine squared x and square it, I get positive sine to the fourth x, because anything squared is positive. Except I suppose. And then I multiply all of the factors on the right-hand side. Cosine squared x stays the same, but sine to the fourth x times sine x gets me my sine to the fifth x. And there's our identity verified. That was kind of a long one, but if you see polynomials, mainly trinomials, there's a chance that it can factor like a quadratic, or in this case like a fourth degree, and you can use some of your identities to change it into whatever you want it to. If you like this video, please subscribe and comment below on any topics you'd like me to cover in the future, and I will be doing more videos on verifying identities with all sorts of identity groups and strategies. Thanks for watching.